Hi, today we are going to discuss about the thermal excitation of magnons, which is also called the block T raised to 3 by 2 law. In the last lecture, we understood that the spin wave can be quantized in a similar way as phonons, and a quantized spin wave is called the magnons. The energy of magnons mode of frequency omega with n magnons is given by these expressions. And being a boson, the average number of magnons excited is given by the Planck distribution law. So that the total number of magnons excited at temperature T is given by these expressions, where this d omega represents, just like density of state, this is the number of modes available within a small interval of frequency d omega. So before going to that, in a three-dimensional, the number of modes per unit volume of wave vector, which is the value less than k, number of modes per unit volume, which is given by this expression, d of k is 1 by 2 pi all cube into volume of the sphere, that is 4 by 3 pi k cube. So that the number of magnons within a frequency d omega at omega, that is d omega, d of omega, d omega is given by this expression, where we are just taking derivative of this term, these expressions, into dk by d omega into d omega, right? Okay. So we have at low temperature only magnons which have low frequency are thermally excited. So this is the expression for the dispersion, from the dispersion relation at low frequency h cross omega is approximately equal to 2js a square k square. So this is applicable at low temperature. So that we can take derivative of d omega by dk from these expressions, and we can substitute here in these expressions. Then there will be one term with k. So again we can substitute for k from these expressions, so that you will get this one, d omega will be these terms. So this can be written in this format. Now we are going to substitute for this d omega, and the average value in this one, that is the total number of magnons, can be calculated from this expression, integral d omega n omega. So we are going to substitute for this d omega and n omega here, and we are going to take integral from 0 to infinity, because the n omega, this n omega, which is 1 by e raised to h cross omega by kt minus 1, tends to 0 as omega tends to infinity, because e raised to minus infinity is 0, right? So this will be the integral will be taken from 0 to infinity. So this will be the expressions, and in order to reduce this one, we substitute for h cross omega by kt is equal to x, so that dx is h cross by kt into d omega. Now we are converting everything into x, so that the summation total number of magnons will be these expressions. So on reducing further, you will get 1 by these expressions. So this is a definite integral, the integral 0 to infinity s raised to half by e raised to x minus 1, that is the value of that integral is 0.0587 into 4 pi square. So the total number of magnons will be this term multiplied, so the 4 pi square will be reduced further, so that this will be the total number of magnons. So as each magnons lower the total magnetization by 1 unit of spin. So that's why the one excitation means one spin reversal. So that sigma k and k represents the total decreasing magnetization. So that is the total decreasing magnetization delta m. And if n represents the number of atoms per unit volume, then n into s represents the maximum magnetization. That is called the saturated magnetization. So that this sigma k and k can be taken as changing magnetization, and ms can be written as the total magnetization, the maximum magnetization. So that the fractional changing magnetization can be represented delta m by ms, that is sigma k and k by n into x. So that will be, from that expression we can return this one in this format, divided by ns. So this delta m by ms will be some constant a into t raised to 3 by 2, and this result is called the block t raised to 3 by 2 law, which is the thermal excitation of magnons at low temperature. I hope all I had tried to make the derivation as simple as possible, and I think you can follow from this. Thank you.